Hello everyone. Starting from this video, we will learn about the joint component. The properties of joints are not as extensive as the base class properties of colliders, but there are some properties that appear in several joint types. To avoid repetition, this section will provide a unified explanation of some common properties and functions that often appear. First, let's introduce joints. Joints are used to connect two or more rigid bodies, constraining them to the physical world or to each other. Joints define how objects move relative to each other, simulating the motion of various mechanical structures in the real world, such as hinges, springs, ropes, pendulums, etc. In LayaAir, a total of 9 joint components are provided. By using different types of joints, developers can create complex physical models to provide more realistic dynamic behaviors for games or simulations. In the joint component, most rigid bodies need to be bound to other body to form a combined joint relationship in effect. The other body property in the joint properties specifies which rigid body the current rigid body should be bound to, forming a pair of joint combinations. In LayaAir IDE, you can select a node with a rigid body component through the pop-up window, or directly drag a node with a rigid body component from the hierarchy panel into the property input field. The anchor point specifies the exact position where the joint connects to the rigid body, telling the physics engine where the joint should act on the rigid body. The default value of the joint's anchor point is at the origin of the node. For example, if the node's default origin is the top left corner, then the anchor point value is the offset based on that position. If you want to set the anchor point of the joint to the center point, it is recommended to directly modify the x and y values of the node's anchor point to 0.5, so that the default joint anchor point does not need to be set with an offset value. Observant developers may have noticed that this joint has two anchor point settings: the self-anchor point and the other anchor point. Regarding the naming of anchor points, some joints only need to set the anchor point of the self-rigid body, while some joints not only need to set the anchor point of the self-rigid body, but also need to set the anchor point of the other rigid body connected to the current joint. When both the self-anchor point and the other anchor point need to be set, to clearly distinguish them, they are referred to as self-anchor and other anchor respectively. When there is no need to set the anchor point of the other rigid body, the anchor point of the self-rigid body is directly referred to as the anchor. In addition to adjusting the anchor point position by editing the values, the joint component also provides a physical auxiliary editing function. By clicking the Edit Joint Connections button, 2 points will appear at both ends of the joint connection line. The red point represents the anchor point of the self-rigid body, and the green point represents the anchor point of the connected rigid body. Taking the distance joint as an example, in the editing mode of the joint connection line, by long pressing and dragging different colored anchor points, you can change the corresponding rigid body anchor point position. When the mouse double-clicks outside the rigid body and node, the editing of the joint continuous anchor points will be automatically cancelled. To edit again, simply click the Edit Joint Connection button. The frequency property also appears in many joints. The larger the property value, the higher the vibration frequency, meaning that a vibration cycle is completed in a shorter time, resulting in a relatively smaller vibration amplitude and faster vibration speed. Therefore, we can understand that the frequency property defines the rate of vibration of the joint rigid body. In some applications, the vibration frequency can be adjusted to simulate different types of motion. It should be noted that the frequency cannot be too low, especially not set to 0, as setting it to 0 is equivalent to disabling the spring effect of the joint, causing the joint to lose its constraint ability. In LayaAir IDE, there are the effect comparisons of frequencies set to 1, 0.8, and 3. Running and observing the effect, you can find that higher frequencies typically correspond to faster vibrations, while lower frequencies correspond to slower vibrations. Damping is generally used to describe the process of gradual energy loss in a system, such as velocity reduction caused by friction, air resistance, etc. It has the same basic physical properties as the linear damping and angular damping involved in the previously explained rigid body, both used to reduce the kinetic energy in the system and help objects return to a stable state when no external force is applied. The difference is that rigid body damping acts on a single object, affecting its linear or angular motion. Joint damping specifically targets to rigid bodies connected together, controlling their relative motion and vibration. Joint damping helps control the vibration and impact transmitted through joint motion, preventing excessive oscillation. In LayaAir IDE, there are the effect comparisons of no damping, weak damping, and strong damping. Running and observing the effect, you can find that the greater the damping, the faster the kinetic energy is lost. Usually, collisions between joints that connect rigid bodies to each other are not required, which is also the default setting for joints. However, there are some cases where there is a need for collisions to occur between the joint rigid bodies connected to each other. In this case, checking the Collide Connected option allows the rigid bodies connected by the joint to collide with each other. It should be noted that even if Collide Connected is checked, the prerequisite for collision is that the two rigid bodies connected by the joint themselves are rigid bodies that can collide. In LayaAir IDE, there are the collision effect comparisons of two rigid bodies with and without the Collide Connected setting. Running and observing the effect, you can find that the two rigid bodies with the Collide Connected setting collide with each other, while the two rigid bodies without the Collide Connected setting do not collide. That's all for this section. Thank you.